Number systems. Hey look, another death by PowerPoint. And once again, in section 9.4.2 is the interrelationship between software and hardware of the software design and development syllabus. This time around we're going to take a look at number systems. Why? Well, it's actually quite simple. All computers use binary data. You might have heard that before in one of these presentations. And because all data in any system can be rendered in terms of ones and zeros, we kind of want to make that more convenient to render. And we do that by using hexadecimal, which renders 4 binary digits into 1. In fact, the stop code you're seeing there is a memory address which is using hexadecimal. And address 0x94E, etc. That's a hexadecimal addressing system. So instead of putting out huge numbers of zeros and ones, we'll simplify it somewhat into this other number system. And hex uses base 16 instead of base 10 like we know for our decimal, or base 2 for binary. Either way, we need to know more about it. So let's have a look and dive in. First thing we're going to do is convert numbers from binary to decimal, from base 2, which we don't really understand, to base 10, which we do understand because we've worked in base 10 for our entire lives. So we start with a number line, and this is always the first thing you should draw when you're doing conversions between numbering systems. Always start with your number line. So when we do our number line, we work out how it's derived. 2 to the 0th power equals 1. 2 to the 1th power equals 2. 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. And so on and so forth. And the number line can theoretically go on forever. What I've got on the third line here is just a random binary number. Literally ones and zeros, didn't put any thought into what the order was, just some numbers. So how can we convert this binary number to its decimal equivalent? I'm glad you asked. So there's my number line again, and the number I put in. We have one lot of 64, so I add one lot of 64 to the total. One lot of 32, so I add 32 to the total. 0 lots of 16, so I don't add the 16 to the total because I don't have any values of it. One lot of 8, 0 lots of 4, 0 lots of 2, and one lot of 1. Simple addition, therefore, 64 plus 32 plus 8 plus 1 equals 105. So I've just converted a binary number to its decimal equivalent. It is really that simple. Start with your number line, add your binary value in, making sure that there is always a value in the ones column, the last value is in the ones column. And every time you see a 1, add the corresponding value. It's that simple. So hey, could I take a decimal number and convert it to binary? Well, yes I can. So here is my decimal number, 168 to base 10. Start with my number line, 128, 64, etc. 128 is the highest value I need, simply because the next value up is 256. Look at what it says here. What's the largest number on the table that can be subtracted from the decimal value and leave a positive result? 256 is too big. 128 is the biggest value that can be deducted, so I add 1 under the 128's column and subtract 128 from my initial value, 168. So 168 minus 128 is 40. So now the remainder is 40. What's the next largest value on the table that can be subtracted from 40? 32. So a 0 goes into the 64's column because there's no lots of 64 in my number. There is one lot of 32, so I add a 1 into the 32's column and subtract 32 from 40. What's my remainder? 8. Well, that's actually quite convenient now because there's no 16s, one lot of 8, and my remainder from there is 0, so everything else is zeros. So I've just taken my decimal number, 168, and converted it to its binary equivalent really quickly, 10101000. It is that easy. Don't think too hard on it. It's supposed to be a simple job. Now I mentioned before we use hexadecimal in computing, and that's to render decimal values more conveniently. It is easy to work in hex and binary because we're taking 4 binary digits and converting them to one single hexadecimal value, and we can read that more easily. They're less unreadable anyway. So hexadecimal is base 16. Now remember, we work in decimal, which is base 10. Hexadecimal is base 16. This actually presents a problem to us. We only have 10 digits in our Arabic numbering system, 0 through 9. So before we get to double digits, we need to get to a value for 15. So we steal the first half dozen letters from the alphabet. So 0000 in binary is 0 in hexadecimal and correspondingly 0 in decimal. But 1111, the highest single integer hexadecimal value, is F in hex, and you'll notice it's 15 in decimal. So we've stolen the first 6 letters of the English alphabet to get around the fact that we only have 10 digits in Arabic, and we've got to get to the 15th individual digit before we get to double digits. It's confusing. 0 through 9, then A through F. Now, when you're working on your binary to hexadecimal conversions, you always start with this table. The binary equivalent of 0, 0, 0, 0, 0, and then count up individually. So 0, 0, 0, 0, 0, 0, 0, 1, 10, 11, 100, and so on. Notice that those leading zeros are always included. And you'll see so far at 0 through 7, nothing changes. Everything's about the same. 1000 in binary is 8 in hex and 8 in decimal. So far, so good. 1001 in binary is 9 in hex and 9 in decimal. They are identical, and this is where things change. 1010 is 10 in decimal, but that's where we get to double digits in decimal numbers, but we're still in single digits in hexadecimal. A, then B, C, D, E, and F. 1111 in binary is the decimal equivalent of 15, but the hexadecimal equivalent of F. The next value goes to 10 in hexadecimal and 16 in binary. So what we've done is we've nicked the first 6 letters of the alphabet to become the last 6 integers in hexadecimal. Don't overthink it, it's really simple. Let's just note some stuff here, okay? Leading zeros are always included. Numbers always start at 0000 when you're doing your binary to hex conversion table. And actually, this is why the first value in most arrays, as defined by programmers, is 0. So yes, 0 is 1. 0 is first. It's a terrible joke, and it also explains quite a bit about why arrays are the way they are. So here's my number, my big long binary number. I've just randomly smashed out some zeros and ones. Yes, it's random. What I need to do if I'm going to convert this binary number to hexadecimal is split it into groups of 4 starting from the right-hand side. And you'll see when I do that, hey, look here, I've got a 2-digit number on the extreme left. Well, that's easy to fix. I add leading zeros. So it's 0010. And you saw the table before had options for 0000 and 0010 and so on. Now I always start from the right and grouping groups of 4 from the right, because if I have to add these leading zeros, if I start from the left, I'll add 2 zeros to the end, and they'll be trailing zeros. They would change the number. They would change the number significantly. Think of it. If you had the number 123 in decimal, and you add 2 zeros to the right, you don't have 123 anymore, you have 12,300. Whereas if you add them to the left, you got 123. So you always start from the right and add leading zeros where you need to. And then I read from my hex table, which I had a couple of slides ago. 0010 is equivalent of 2. 0101 is 5. 0110 is 6. 1001 is 9. 0010 is 2. 1010 is A. 1110 is E. 1011 is B. So this big long binary number is 25692AEB in hexadecimal. Could I convert this massive number to decimal? Actually, yeah, I could. My number line would be huge, and I'm not going to do it. Well, yes, I am. 627 million. But you won't be asked to do that in an exam. If you can do a number much smaller than that, you're still demonstrating your skills. So yes, you can convert very large binary numbers, very large hexadecimal numbers, to very large decimal numbers. What about binary to octal? Well, octal is base 8, which is conveniently 3-bit binary. The octal table is very similar to the hexadecimal table, but easier because it's only 3 bits long. So you start at 000 and you finish at 111. So when I create my octal table, it looks like that very simple table on the right hand side. And when I'm converting a number from binary to octal, instead of splitting into groups of 4, I split into groups of 3, starting from the right hand side. And once again, I've added a leading 0 here because I had a group of 2 at the end. So 010, that value there is 2. 101, so that value there is 5, and so on. And so therefore I've taken my number from binary, converted it to octal, really simple, in one easy move. Now this means that you can convert values from binary to hexadecimal to octal to decimal. And in fact, it's quite easy to do. Follow the steps. Step 1, draw the binary binary number line, Second, draw the hex conversion table. Third, draw the octal conversion table. That's it. Now this is the last slide in this part of the presentation, so I'm going to leave this going for a moment. You should be able to copy this table into your workbook and do those conversions. The binary value becomes 1001 is 9 in hex. 0100 is 4. So the hex value of 10010100 is 94. The octal value is 100 is 4, 010 is 2, 010 is 2, so that's 244. And the decimal, again, working through the number line. I can't work it out off the top of my head as fast. So draw this table up and see if you can do those conversions. Very best of luck to you.